Let's do a more involved problem here. We're actually going to use the definition of inverses to determine whether f and g are inverses. So the definition of inverses is that when you compose two functions and you get x, and then you compose them in the other direction, and again you get x, then g is the inverse function of x. And likewise, f is the inverse function of g, which in other words means they undo each other. Okay, so what do we mean by undo? Undoing, what we mean by undo is that if I started an x value and use f to find some f of x value, and then I take that f of x value and I pass it through the function g, and on the other side g of f of x turns out to be x, I have just, undone the work that was here, has been undone here to arrive back at x. And that should work the same way if they're inverses, meaning that if I start going the opposite direction and say, let's take x and pass it through g, so I'll have g of x, and then I'll pass that through f and get f of g of x, and then that will give me x. So again, the work that is done here by g gets undone by f here, and we end up back at the same x value. So it's a very circular relationship, and it's another way of looking at it. Like if I say, here's my f of x function, and here's my g of x function. If they're inverses, then there's some x value that I can put here, and then I can take that result and put it here, and it'll get me back there. And it works the other way around as well. Yeah. So to figure out for all values of x, right? So f of g of x equals x, and g of f of x equals x for all x values. The all part is very important. And the only way to know if it works for all of them is to use an algebraic solution so that I will know in general for any x value. So what I'm saying is I can't use a concrete example with numbers and let that be sufficient. So for instance, if I said, well, let's plug in 0, let's let x equal 0, then f of 0 will give me, see, negative 4 times 0 is 0, plus 9, so that'll be 9. So I get this coordinate on the function f. And then if g is the inverse of f, then g of 9 should give me 0 back, right? And let's see what happens here. If I plug in 9 to here, right, it's not going to 0 out. So that's not true. So I could say F and G are not inverses, and because I've been able to find an x value for which g of f of x is not equal to x. Right, so that's kind of like proof by a counterexample. And that works because it has to be true for all x values. That does actually prove that f and g are not inverses by using that specific x value to test it. However, that's not really good enough in every case, because if they had, it's possible that there might be some value where that would work, where you could pass a value through f and then pass that result through g, and then you would have x back again. Let's say that happened. Let's just say, just for the sake of argument, let's just say I used 3, and 3 mapped to, I don't know, 4, and then 4 mapped back to x again, or back to 3 again through g. If that were to happen, and I was to say, yeah, f and g are inverses because 3 maps to 4 and then 4 maps to 3, that would not be sufficient, because that would only be one instance in which that kind of outcome happens, and it needs to happen for every single possible x value. So I would have to try to go through every single possible x value, which is impossible, because the domain of f of x, since this is a linear equation, a slanted linear equation, this actually has a domain that is infinite. It's negative infinity to infinity. There are no limitations on x. So I would have to test every single x value, and that is just simply impossible. So if you can find a counterexample to show that they're not functions, great. But if you don't, you have to be able to show it in general. So showing it algebraically looks like this. Is f of g of x equal to x? Let's see. Negative 4 x plus 9. Then plug in, that's the f function with a space left where the x normally is. And then I can put in the g function, negative 1/4 x minus 9, and then I have to distribute this negative 4 here, so I will have positive 1, and this will be 36, and then I'll bring down the 9, and this will, oh, I forgot my x right here. This is an x. Yeah, so this will equal x plus 45. So it did not result in x. So now for that in general, I would be able to say, no, they're not functions, or they're not inverse functions. Now, because it already failed in one direction, I don't actually need to do the other direction, but I'm going to simply so we can see both sides. So g of f of x is negative 1/4 times x minus 9. Plug in the f function, negative 4x plus 9. Right, so what's going to happen is this gets distributed and I get positive 1x. This gets distributed and I have negative 9 over 4. Bring down the other negative 9. And this is not going to zero out. So then this whole thing is not equal to x. And again, we're shown that they are not inverses. Now, let's look at an example where they are inversely related so that you can see that as well. So let's try doing f of x equals 2x plus 3 and g of x, I'll do it with purple, g of x equals x minus 3 over 2. So we'll test f of g of x okay, so what's going to happen here? The 2 distributes, or actually let's just cancel it out with this one. And then we have x minus 3 plus 3, which is x. So it worked so far, but we also have to check the other direction now. So it was supposed to be x minus 3 over 2. And then plugging in the f function, 2x plus 3. And I'll start by canceling out the positive 3 with the negative 3. And then the 2's cancel, so I do get x. Very nice. See, works in both directions. All right, so the strategy should be, if you first check one direction and it works out well, then you go ahead and you check the other direction. However, if you check one direction and it does not work out well, then you don't even bother doing this because it would be a waste of time because it has to work for both, right? So that's the strategy. So let's see if we have another example we can do. I'll do that in a new video though.